Jugglebot is back together again. Oh, the camera didn't change. Damn it. Bloody OBS screw me around. Yeah, my grand reveal was kind of ruined then, but that's okay. But yeah, Jugglebot is finally back together again, and I am very glad about this. The process of putting Jugglebot back together was fairly uneventful. I took the opportunity to give everything a good clean, a good wipe down everything, and Jugglebot, the base is looking cleaner than it has for quite some time. I don't know if this camera is really going to show it very well, but everything is nice and orderly down there, which I'm a big fan of. Not much dust down there, and hopefully my little protector thing keeps it that way for some time. Yeah, there was, before I get to the only problem that came up in the entirety of the construction, I did also change the hand spool over from the old 3D printed one to the new aluminium one. And the 3D printed one, I am going to be taking some videos of like what the new one looks like, but even for the old one, or when I had the old one on, I could, once I was, I don't know, being a bit more critical of the printed design, I could pretty easily discern that the string was not perfectly uniformly running up and down the spool. So I don't know, I have, and like once I replaced it with the aluminium one, it was much smoother. So I'm hopeful that I haven't actually like run anything through any actual movements yet now that the robot's been put back together. I'll talk about why in just a sec, but I have high hopes that this spool will not cause me any problems anymore, which will be lovely. I'm keen for, yeah, all problems to be gone. Yeah, the only problem that did come up during the reconstruction of Jugglebot was that for some reason the threaded insert that was inside this part, which is like the final stage of the universal joint that's on the end of all of the legs, for some reason in one of them the thread was like super munged up, and just like I could get the shoulder bolt in like halfway, but then there was just something in the thread that was just stuffing it up. And this was like the second last actuator that I had to put on, and at the time I was just kind of like, this only needs to go on once. If I can just kind of like brute force it in, then I don't need to worry about it anymore and the problem will go away. But unfortunately, I could not get it in the whole way. And it was, it ended up getting, so the shoulder bolt thread was stuck in the threaded insert, and eventually it reached a point where it just sheared the threaded insert from this part here. So you can see there's a nice big munged up hole there because it just started slipping, and then it was all gone from there. So unfortunately I had to figure out a way to remove that, which wasn't trivial, but with a good pair of pliers and a firm grip, it was doable. But yeah, I had to reprint one of those parts and then wait for that to print, and then that delayed me another day. So I did all of the reconstruction on Wednesday. That delayed me until Thursday, and because I'm using Loctite, the Loctite suggests that you wait for 24 hours for it to fully cure. Now, granted, in this situation, I probably didn't need to wait for the full 24 hours. I probably don't need like maximum strength from these connections. But on the other hand, I don't want to disturb that bond and have it loosen a little bit and then set in the looser state, so there's a bit of slack, a bit of wobble in the joint. So I figured I'd play it safe and give it the full 24 hours, which to be honest is probably like right now. But yeah, so I couldn't do any actual testing of the robot now that it's been back together. I have like moved it around by hand and everything seems fine, but yeah, I haven't actually run it through its paces yet, which I'll hopefully do, or I will do, either later today or next week, which I'm very keen for. I am very anxiously waiting to do the testing with the motion capture cameras to see how much more accurate it actually is. Yeah, I'm going to be very, I don't know, disappointed, frustrated if all of this leg testing has had like no benefit. Yep, but we'll get there when we get there. We'll cross that bridge if we come to it. Hopefully we don't. Yes, so let's get into it. We have some new things this week, but before the new things, we have, of course, a fun tangential thought, which this week is juggling big concrete spheres. And this is something that I think it's in my mind, it's somehow related to the Three Body Problem book, because I read that series a little while ago, and it is still my favorite fiction series ever that I've read. It is phenomenal. If anyone has not read it, I strongly, strongly recommend it. It is so good. The first, it just gets better and better and better. So if you're a bit like kind of caught up in the tedium of the first book, don't worry about it. Just keep going, and it just gets better. But there's nothing specifically in that book where they're talking about juggling big concrete spheres or anything. But for some reason in my mind, this is related. Maybe I came up with this idea around the same time as when I read it. But the idea here is that I just think it would be phenomenal to have enormous spheres, like ones that are obvious, like you can just look at it and be like, that thing is insane. Like the ones that like the big like Norwegian like strongmen lift and like put on top of the barrels, that sort of stuff. Like massive, massive balls, and just having them glide perfectly through the air. I think that would have a certain level of like immensity that if you saw that in person, you'd be a bit like, whoa. Like, I don't know. I think that'd be very, very, very cool to watch. And then of course, like, we don't necessarily need it to be made of concrete because that's obviously quite heavy and would be more difficult to throw around than other balls. But like beach balls and like just like giant balls, I think would be cool. I think beach balls it definitely loses that immensity. Like if you can see it sort of like floating through the air, I feel like it has to have some weight to really be like, whoa, like that's intense. But yeah, something along those lines. And I think that the Stewart platform based design, in my mind, would be fairly suitable for this sort of juggling, because it's like all of that force is getting distributed between all of the 6 actuators, or even honestly a cable robot might do just as well, because that force is equally being distributed between multiple actuators. But yeah, I think that'd just be super sick. But yeah, obviously this is one of most of the things, like the extra tangential things that I've mentioned, I have imagined happening in like my lifetime. I'm not sure about this one. I don't expect that I would have the desire to push for that once Jugglebot reaches its other goals. I think I would prefer to move on to other things. So unless someone else at some point in like 30 years is like mad keen on getting this specific thing to happen, I'm skeptical that it will happen in my life. But it'll be sick eventually. But yeah, one day. Yes, so one other thing that I want to get into before showing the new stuff. Also, by the way, this is probably going to be a fairly short stream because I've had some other things to do this week, and yeah, the construction took a while and there's not too much to say about that. So yes. But yeah, one other thing that I do want to mention is digging a little deeper into the data analysis of our leg movements. And big thank you to Mikkel. I'm not going to try to pronounce your last name, something Swedish, I think. Mikkel suggested that last week when I presented the data of the leg actuator testing, I noted that, well, you could see in the data that for the first couple sequences, like the extend and then home and extend and then home, and then the sinusoid thing, for those sections, the difference between the error between the measured position and the commanded position was fairly small. But then in the last section, where I got it to extend and then go down to like 25%, and then extend and go to like 50% and so on, it was like holding the intermediary positions. On those sections, the error was quite a bit larger. And Mikkel was suggesting that I should prune my data down to only, if for the purposes of like setting the calibration values of like how many millimeters is in a revolution, sorry, how many linear millimeters is in a revolution of the motor. When I'm getting those calibration values, I should prune my data down to only be looking at the data that is concerning the ranges that I mostly care about, which should probably be between like 20% to 80% of the actuator's extension. I think it's uncommon that any actuator will be going below, like between 0 and 20% extended, and then between 80 and 100%. Just because in normal juggling, we're going to be trying to keep the platform in its like safe zone, so it's not really going to be pushing out really far to the extremities of its workspace, for now at least. I really, really don't want to break any of the actuators, so I would like to keep it as safe as possible. And like for juggling like 2 or 3 balls in one hand, if you can throw accurately, you really don't need to move very far. You just need to move by like the diameter of the ball, maybe plus like 10% if you want to account for a little bit of error. So it really shouldn't need to move very far when it's juggling by itself. So yeah, Mikkel's suggestion was a very, very good one. And to implement that, I have pruned the data down to only include just the first like extension, home, extension, home, extension, home. So I could also limit the position values so that it's stuck between like the 20% to 80%. But I don't know if that's going to make too much of a difference, because the main sources, the main location of the error is during those sections. So I think including like the bottom section down here and the top section up here, I don't think that's really going to have much of an effect. But so that got me thinking about other things that I could do to improve the data analysis here. So you can see at the top, I've got on the title now, we can see what piece of data we're looking at. Also, by the way, if you are interested in any of this data or the way that I've analyzed it, all of the code and the data itself is on GitHub, and there's a link in the description of this video if you want to check it out. Yeah, so I was thinking of other ways to improve this, and you can see in the title, I've got simple scaling factor. And this is the way that I have been scaling this data the whole time, every time I've shown it to you. And what that involves is we leave the red line, the linear scale data, the measuring data, we leave that as it is, and then we just take the maximum value of the motor position data and then scale that so that it matches the maximum data of the linear slider. So we're just basically picking the maximum of each and then raising it so that both of those maximums are the same. And in my mind, that is like the most straightforward way that I could possibly do this. Like, it's not even looking at, it doesn't even consider the rising stage at all. It's only looking at just the maximum. And also, by the way, this is after the 0 points have already been aligned. So they're already both like aligned at the start. And I was like, well, that's a super basic thing. And if there is any erroneous peak in the motor data, like it could just be this little tiny bump here. I don't actually know what the maximum for this one is, but it could just be that little bump. Like if that little bump was a bit bigger, then that could really mess up this scaling factor and would throw the whole thing off. So I thought, okay, I'll do a slightly more sophisticated approach, and I'll show you on a different one because that one wasn't a good example, nor is this one. I'll show you my code as well while I'm doing this. Okay, this one's better. So my idea here was that rather than taking the absolute maximum, instead we can take the average of the position when the slider is at the very top. So the actuator has fully extended, it holds its position for, I believe, from memory, it was 1 or 2 seconds, and then it goes back down. So I was thinking, when it's at that held position at the very top of its stroke, we can take the average of those positions, of like the linear slider position and the motor position, take the average of all 5 of those, and then use that to construct this scaling factor. And so we can see here, these gray dotted lines are the start and the end of the period that we're averaging over for each sample. So we're basically taking the average of all of these gray sections for both the red and the blue data. And I would have thought that would lead to a more accurate scaling factor, so that way we would have, on average, less error throughout the entire data set. But that's not how it worked. So I'll go into a little bit more detail with that analysis in just a sec, but I want to show a summary of what I've found. So keep in mind as well, don't forget that we have 2 sets of data for each actuator. We have a set where I had the testing rig vertical in like the in situ-ish situation for the actuator. So everything was vertical. The big problem with that is that because it was all vertical, I couldn't really support the measuring stand super well. So it was wobbling a little bit at the start and at the end. When the actuator was starting to push or pull, the whole tower would kind of like shift a little bit, which I thought was like a no-go, and that was adding to the sources of error here. And I was like, okay, that's terrible. I'm going to do a horizontal test. So we also have a second set of data for every single actuator in the horizontal case, where the entire testing rig was clamped down onto my desk and there was no movement at all except for the actuator itself, obviously. So I've gone through all 12 data sets, so 6 actuators, horizontal and vertical, and I've looked at both the simple scaling and the average scaling, and this is what I found. Is like, so what I'm about to show is the data set and type of scaling factor that has led to the smallest mean error and standard deviation error. From memory, all of them had both of those error data were, like the results were lower. So like the mean was lower and the standard deviation was lower. So for the first actuator, this is like the horizontal data is the more precise one, which is like, okay, cool, that makes sense because the tower wasn't wobbling around. But then the simple scaling factor was the best one. Even, well, although the simple and the average are pretty close together, so they're not too far apart. And for reference here, I can show you what that actually looks like. So, for some reason it's not printing. We can go to 0 horizontal. And we don't really need the plots. Why is my... Oh, it's scrolled all the way down. That's so weird. I've never had this happen before where it's not printing. It should be printing. Let me restart VS Code. It doesn't really matter too much, but yeah, they're pretty close together. So then, Actuator 1, the vertical loading case was better. There was less error in the vertical case with the simple scale. Actuator 2, horizontal, simple, but again, they're close together. And this one has a good display of something which I'll talk about in a sec once VS Code reboots. Are we printing now? Yes, okay, cool. So we can see here, this is for, I've made it actually print the one that we're actually looking at as well. So this is horizontal rig, the 0 data, and we can see the simple scale, we've got a standard deviation of 2.2702, and then for the average scale, 2.2791. So they're very close together, like it's, what, the third decimal place off. So that, yeah, they're super, super close, but still slightly different. And they do give slightly different scaling factors that we would use to actually control the actuator. And for reference, this is where the averages are. So something that I haven't really mentioned is the way that I have determined where these kind of bands should be that we're looking at. And originally I was like, oh, we can be really fancy and we know that it's going to be pretty, like we know that these, we want to be averaging over the period where there is no change. So the actuator has like stopped and paused. So we should be able to use like some kind of fairly sophisticated data analysis process where it just says, okay, data hasn't changed by some threshold over the last half a second or whatever. So let's take that as our first window and then look for the next time when that's the case. And we are above a certain threshold so that we're not looking at the bottom ones as well. And then, yeah, just do that for all 5 peaks. But that wasn't working. I think part of the reason is because despite the fact that this looks flat, it's not actually like flat. I mean, I guess I could just set the threshold to be what, like 0.1 or 0.5 millimeters or something. That would probably work. But I couldn't get it to work and it was just frustrating me and I wanted to just get it done. So instead, I just did it manually. And I was thinking, okay, cool. Because all of these actuators ran the exact same procedure where they would do the exact same motion, I didn't change the code at all between all 12 of these tests, they should all have the same time. So we should be able to say, band 1 is between this time and this time, band 2 is between this time and this time, and so on for all of them. But unfortunately, they did not all go at the exact same time. So like here, for the 0 data, we can see that the bands are in pretty solidly in all the flat regions. But then if we look at, for example, 5, they don't line up. Oh, maybe it's the vertical one. Because that one was actually pretty close. Oops. So with the vertical one, yeah, it's all the way off the end. So here, I don't know why. Maybe it was because this had to, like, we had to push against. No, that doesn't make sense. I'm not really sure why, to be honest. these are slightly different. Something caused the actuators to run a bit faster. I don't know. Maybe I did change the code between the vertical and the horizontal ones. I don't remember, but yeah, so we can see that the window is now pushed off the back. So it's a very naive approach, and not for all of them, the window doesn't exactly match up perfectly with the flat region. But I'll talk about that more in just a sec. So yeah, I'll talk about the good display of difference thing in a sec as well at the end, once we get through all of them. So for 3, vertical simple is the best, which is like, why? Like the tower was wobbling everywhere. Why is that better? 4, vertical simple as well. And then 5, vertical averaged, which is the one that I just showed. So this has less error than the simple scaling approach, even though this window is averaging over these data in here, which is clearly not the peak. So what? So yeah, it seems like having a lower scaling factor leads to less error. But I think part of the reason why that is the case is because for all of these samples, we see that the motor on the way up and down, which you can see is that's where all of the error is happening, just on the up and then just on the down. At the top and bottom, it's not so much. So I'm thinking the reason why this is showing a lower overall error with a lower scaling factor is because the motor data is higher than the measured data, for a reason I'll talk about in a sec. And so by having a lower scaling factor, we're kind of like compensating for that. Now, the reason why I believe this is happening, where like the motor data is above the measured data, or the linear data, I believe is because of the slop in the actuators, basically. So at the very beginning, the motor starts to spin, the string is starting to take up the tension, it's taking it up, taking it up, taking it up, and then eventually it's all taut, everything, all of the slop is gone, and then the actuator actually starts to move, like the linear part actually starts to move. And that, of course, means that the motor position is going to be ahead of the measured position all the way up until the very end, when they meet up again. Well, in most of the cases, they meet up again. Like, let's look at the average of all of these. Okay, yeah, no, because we've scaled it with, we can look at this one. The simple scaling, they do meet up pretty closely. Yeah, so I'm thinking like maybe because of that offset, like having a lower scaling factor will be less erroneous during the movement phases, which is kind of artificial, but also kind of legit, because when Jugglebot's actually working, it's going to be spending a lot of its time moving around. And if we are ever needing it to be in a precise position while the actuators are moving, it could be better to use a lower scaling factor to compensate for this stretchiness. But then if we're trying to get Jugglebot to be really precise when it's still, we maybe would want a slightly different scaling factor, so that once the Jugglebot is stationary, all of that slop has gone away. It could be like elasticity in the string as well. So like once the actuator has stopped moving, that elasticity continues to extend the actuator just by like that little bit more until that elasticity is gone, and then it's at its like correct position. But whatever the case is, it seems like the actuators are behaving slightly differently dynamically as they are statically, which makes it a bit annoying to calibrate them precisely. Yes. The one other thing that I wanted to show is for actuator 2, the horizontal data. And yes, so here, it doesn't really matter which scaling factor we look at. Here we can see there's a massive, massive difference between the positive error and the negative error. And this is equivalent to, or like this is, indicative of when the actuator is extending, we're getting this positive error, and then when the actuator is contracting, we're getting this negative error. And I believe it's for the same reason, where the motor starts to move down, and then it pulls the string, pulls until all the tension is gone, or the slop, or whatever it is all gone, and then the actuator, the linear part, again starts to move. Which does put the motor position data below the linear slider position, which, I don't know, they seem to all be slightly different. And I think, and so this is, yeah, what I wanted to point out here is the fact that for this particular actuator, there is a lot more error, like double, on the downstroke versus on the upstroke. And I believe that this is related to the fact that there are actually 2 strings in each of the actuators. It's not just one continuous string, even though it could be, and it probably should be if I knew that that was a possibility when I was designing this. But in any event, there's actually 2 strings in there. So it could be like there's a separate string for tension, for extension, and a separate string for contraction. So it could be the case that, well, this is suggesting that it is the case that the 2 strings are not both perfectly tensioned, so that, like, for example, if the extension string is really nicely tensioned, but the contraction string is not, then the tension could be really precise and nice, but then when we go to contract, there's a bit more give in the system before it actually starts to come down. This one is the most egregious example of that. Most of them are pretty closely mirrored on the top and the bottom, but for this one in particular, the contraction stroke was way more erroneous. Which, again, I don't know. In my mind, this would suggest that I could go into the actuator and like retension that string, but I checked all of them when I was going through this process and they all seemed approximately equally tensioned. I don't have a good way to actually measure that tension. I was considering making a like device, a tension gauge sort of thing, like how you measure like your bicycle spoke tension, which is basically like there's 2 pins and then there's like a spring-loaded pin in the middle, and you put 2 pins on, like you have, let me draw it. Using my hands can only get so far. Let's go to this. Get out of here. So you basically have, if this is your spoke, you would have a pin here, these should be touching the spoke, and then another one here, which is trying to push this way. And there's a gauge in there that measures the position of this pin. And then, of course, because the spoke is not infinitely stiff, it will bend a little bit. And so then you can measure how far this has deflected, and that will tell you that you won't, unless you know like a lot of the material properties of the thing that you're testing and like the cross section and stuff, you won't necessarily be able to calculate the actual tension in like newtons or anything. But you can get a benchmark value that you can then use to compare against other spokes or strings. And I was considering making this so that way I could just check that all of the strings are equally tensioned, but I ended up just kind of going for the old like twang and listen to it test. And yeah, it's hard to get it to be really. I think that would be a rabbit hole that would take more time than I anticipated that it would. Yeah. Something else that I have noticed that I don't think I've mentioned before is that the tension on the strings on the actuator is actually different at the bottom of the stroke and at the top of the stroke and in the middle. So if I have it'd be great if I had one on my desk like I did last week, but unfortunately they're all in Jugglebot now. Yeah, if the actuator is like really, really compressed or contracted, then the string might be particularly tight. But then if I bring it out to like the middle section, it might be a bit more loose. And then if I bring it out to the end, the same string, this is always measuring like the contraction spring, will be tight again. I'm not 100% sure why that's happening, but I think it could be to do with the fact that the final pulley before the string wraps around on the spool is free to move up and down on its on the axle that it's on, but that axle is a threaded bolt, so I don't think that the pulley is really that functionally free to like slide up and down. So really, I think that pulley just stays in one spot. And that means that as the string winds and unwinds, the angle that it makes with the spool changes. So that length of string is going to change, and of course that's going to change the resulting tension. Maybe. We've got some comments. Lawless, hello. Hope Poland is treating you well. Regular Ben says, oh neato. You could try and use that for your use case. I'm not sure what you mean, DE Coder. Yeah, so the TLDR is that these actuators are weird. Yeah. Yep. They're very strange. And I'm still stuck in the same kind of thought process that I was before of like, I don't know which of these data to use as the actual scaling factor because I have to pick one at some point. soon, very soon, once I actually get Jugglebot to move around, I have to pick something. My thinking right now is still just to pick whichever data set has led to the lowest error. It feels kind of, unless I have a good reason to pick something other than that, that's what I'm going to do. Which for more than half of the actuators is taking the vertical data set. It's like I could have saved myself all the time with doing the horizontal rig if I just did the vertical one anyway. But yeah. Yeah, no, Coder. YouTube is very funny about links to external sites. You can try, if you're on Zulip, you can send it to me on Zulip, or like my email is on my channel. If you go to my channel, you can find my email, you can send it to me there. Or YouTube comments tend to kind of work all right. I think there might be more heavy moderation on the live stream comments. We can usually kind of sneak in some in the main video comments. There is one other thing that I want to mention about the deconstruction and reconstruction process of Jugglebot, which I will elaborate on more at the end of this stream. But that is that one of the bellows has finally given up. You can see, I don't know how well this will come across on camera, but some of the quality of this one was not fantastic. And yeah, you can see it more on the inside. Look at that, there's holes all throughout that. So it's not too surprising that this broke. I actually think that this broke a while ago. I've noticed for some months that a couple of them have been looking not too great, and they had like splits in them. And I just kind of put it out of my mind and didn't really want to think about it too much. So I think that this actually might have broken like months ago and has had no negative effect. So I guess the rotational inertia of the motors is not so much to actually move the actuators around. But in any event, this one's broken. So I've completely just removed it. There is another one that is very close to being fully broken if it isn't already. And yeah, they definitely didn't hold up to the removal and replacement process. Yeah, very well. So I'm a little bit annoyed about that because as we all know, I am not going to try to print these again on my current printer because that was a waste of time. I spent so many hours trying to print those and it just did not work. But yes. Okay, so yeah, that's where I'm at with the data. I am just very hopeful right now that things will be better once I use the least erroneous data, get Jugglebot to move around, and hopefully next week's thumbnail will be a nice, clean, smiley face. Fingers crossed. Alright, so now for some new things. The first I kind of teased last week, which is that I have been looking at new linear actuators. And why can't I see? Sorry, there we go. Yeah, so I'll show you the CAD first, and there is a link in the description for this CAD as well if you want to check it out. So this is what I'm thinking. Everything is going to be based fundamentally on a piece of aluminium extrusion, and there are many variants of this design that I think are very possible, and I'll go into those in more detail in just a sec. But the fundamental, like the backbone, is the aluminium extrusion. And then on either side of that, we have two linear sliders. And this is just for this particular instantiation of the design. So again, I'll talk about other variants in a sec. So we have two linear sliders that slide together. One possible concern that I have immediately off the gate right here is that both of these will need to be very carefully aligned. I don't have much practical experience with doing that sort of thing, so I don't know how easy or hard that's actually going to be. My thinking is that we can just put in the bolt on the very bottom one and then like do that up tightly, like with both of them being joined together like this, and then keep the rest of the bolts loose so that way both of these guide rails can like swivel around, and then slide this all the way up pretty much to the top and then do in the top bolt. And in my mind, that should mean that they're both perfectly lined up. And then, of course, go through and tighten up all of the other bolts in the middle. But yeah, so that will that's actuated in basically the right now, in this version, it is actuated in the exact same way as the hand actuator on Jugglebot right now. I only just added this component in last minute this morning just to kind of like complete it. So like the string line is not perfectly, I don't know, designed right now. Like this pulley should probably have to be in a slightly different position. But then yeah, the string goes up, around, up over here, there's a tensioning mechanism in here, which is identical to the one that John designed for the current hand actuator, where this is currently fixed in here on the CAD, but of course this hole is threaded. So if you want to add more tension, you just loosen up these 4 bolts on the side, extend this bolt out with a nice convenient hole in the top, and then bring it out. And then once you've got the right amount of tension, you can redo these 4 bolts on the side. And I love this tensioning mechanism. I think this is so clever. John did a very good job of designing that part, because this means that for every millimeter that this raises up, you're actually extending the string length by 2 millimeters. So it's like a kind of like magnifying effect of like how much tension you get for how far you extend this part out. It's very, very nice. I am a big fan. Of course, the string will then come down and attach onto this part in some fashion. Unfortunately, I didn't have as much time as I would have liked to like fully flesh out the CAD of this design. I got a bit distracted with some other stuff last weekend, but it was good distraction. It was doing productive things that were just not this. So yeah, there are a lot of fine details here that need some work, but hopefully you can get the general idea. The main reason why I'm sharing this now in its incomplete state is that all of you have historically been extremely useful in troubleshooting and in just coming up with different ideas for how these things work. And I think the earlier that I introduce it to the world, the more quickly I will get feedback, and the less likely it is that I'll go down the wrong rabbit hole. Like, I am fairly certain that if I had done this same process for my current linear actuators, I would not have made a lot of the mistakes that I did, such as having like 3 pulleys for every single direction. So for extension, there are 3 pulleys between the spool and the actual linear axis. And then for contraction, there are 3 pulleys. But you don't need 3. I had convinced myself that it is mathematically necessary to have 3 pulleys, but it's not at all. You just need 2. And so many people, that's probably like the most, like the median comment on that YouTube video is, you don't need 3 pulleys, you only need 2. And as soon as I saw like 2 of those, I was like, oh shit, you're right. I could have removed like, what is that? 1/3 of the number of pulleys. Yep. So yes, if anyone here sees anything silly that I'm doing, please do let me know, because that will save me some stuffing around. And yeah, so then on the outside, of course, like right now, this is just a slider and it's like whoop-de-doo. On the outside will be either a circular or a square tube of some sort. And my hope was that I would use carbon fiber, because carbon fiber looks real sexy. But it turns out that carbon fiber tubes of this size are not only very hard to find, in Australia at least, but they're also extremely expensive. So I'm not sure that I'll stick with that. I want to finalize the design a bit more, and then work back and forth between what I can actually buy versus what can fit, because I can't really go too much more tight than this. This is already pretty close. Yeah, so this is one version of what this actuator will look like. The cool thing about having this all based on a aluminium extrusion is that it is extremely flexible and easy to change around. So last week I mentioned that there would be lots of variants of this design, and you could make it very small and also very large. And what I want to do there, I'm thinking of having several different versions. And there's different kind of axes on which these versions differ from each other, but in terms of the way that the motor movement is getting transmissioned to the actual linear aspect, the one option, which is the one that I just showed, would have a string and the motor is mounted onto the actuator itself. And this is exactly how the hand actuator is working on Jugglebot right now. And that is good, but of course, if you had some use case where these actuators are moving around a ton, then you may not want the motor to be actually mounted onto the actuator. You might want to save some weight and have the motor somewhere else. But in some use cases, it might not matter so much. Like for me, for Jugglebot, if I was to use these actuators, I would need to figure out some way to, I don't think this would be too tricky, but I would definitely need some way to turn this lower section into a ball joint, which, I don't think that'd be too hard. And having the mass of the motor and the O drive here, again, we don't really need the O drive, because the O drive is just here because the encoder is on it and it's just easy. But even if I had like a big bulky motor like the ones that I've actually got on the legs right now, I don't think that'd be too big of an issue because it's so close to the bottom. And for Jugglebot's use case, this thing is just kind of rotating around like this. And the fact that there's more mass there shouldn't really matter too much. But in some applications it might. So another option would be using a string actuation, but with the motor connected via Bowden tubes. And you may remember, if you've been following this project for a little while, my older linear actuators had exactly this, where I had Bowden tubes going up to the actuator itself, and then those went around and the motor was actually held in the base of Jugglebot. And I had some problems with that. I think that the majority of the problems, if I was to like look back on them retrospectively now, a lot of the problems were just due to the implementation that I used when I made this. I have since learned that you can get effectively incompressible Bowden tubes, and they're used for like bicycle brake lines and that sort of stuff. So if I used incompressible Bowden tubes and like good string, like the Dyneema string, I think that this could work a lot better. And this would mean if the motor was removed and was only actuating the actuator remotely via these Bowden tubes, that would mean that there's nothing in here that is that sensitive to things like water. So you could move potentially. I will have to do some testing on this to see how like well the linear rails and stuff hold up to this. But you could have the actuator completely like somewhere else, and then the motor and all the electronics and everything can be in one space, and the actuator itself can be in a different space. So that could be very useful, I imagine, for certain cases. I have a feeling this would work underwater, at least for a while. Maybe not in salty water, but I think that would be potentially an interesting case. And I actually remember possibly the reason why this comes to mind is that there haven't been very many people who have told me that they've built the current Jugglebot actuators, but one guy notably has, who was doing from memory, he was making basically a Stewart platform underwater for some sort of research. I don't remember exactly what it was. If you go on the printables and like find my actuators on printables, you can see his comments in there. He's talking about it a bit. But yeah, he obviously didn't want to use these actuators themselves for that purpose because all the motors and everything are in there, but he just wanted to like get an idea of how I did it so that he could then build upon that for his own ones. And if these can just work out of the box underwater, that's a whole use case right there. He wouldn't have had to design his own. He could just take mine and then continue with his research and not have to worry about this side of things. James says, the more parts between the motor and the actuator, the more opportunities for play to enter the system. Yes, definitely. But I do think that if there were good tensioning mechanisms and things like incompressible Bowden tubes, I think that it could be done. I think it could work. Like, I don't know how many modern humanoid robots are string actuated, but I've seen in the past quite a few that were, and they seem to work pretty all right. I have also then, on the flip side of that, I've heard a lot of horror stories. A lot of the comments on those sorts of videos, people were saying, oh, this is all well and good, but as someone who has worked on Bowden tube systems in the past, I can tell you in like a year's time, they're going to really be hating that decision because they're going to have to tension all of the strings. So yeah, pros and cons. In my mind, if the tensioning mechanism is easy to access and works well, then that covers a lot of the negative effects of using this sort of like Bowden system, I think. Joe says, what about an enclosed flex shaft like an RC boat prop to remote the actuator? Yeah, those are interesting. Some people suggested those on the last actuator video. So these, for anyone who's unfamiliar with them, my understanding of how they work is that you have like a bunch of fairly stiff wires, like piano wire sort of things. You have these wound around each other so that they're like, they together are just like a single cable. And then that cable itself is quite flexible. But if you try to twist that cable, because all of these little cables are like stuck to each other and they can't move away from each other, so they're in like a sheath of some sort. If you have that cable bent and you twist it, the same twist will be relayed onto the other end, even though the thing is angled. And you might see this in, I actually used to have one of these for my screwdriver so that you can screw in screws at an angle. So like if you have a screw in here, like for example, I did this, you can't quite see from here, but one of the things that I screwed into the wall over there is very, very close to the roof, and I couldn't get my drill in that close to the roof. So I got this little flex spline thing, put the screw side into the screw, and I could have my drill like down here, and I could drill. Unfortunately, that was in the instance when I actually broke that flex spline because the screw got stuck and I kept going and the thing snapped. So they're good up until a point. And that is an interesting idea, but that's transmitting torsion rather than linear movement. And in my mind, a good aspect of the Bowden tube design is that all of the rotating things are over here, and then all of the linear things are over here. And the Bowden tubes convey that linear motion perfectly. Like that's the main job, is just to convey that linear motion. But if I was transmitting a rotational motion, then I need some way to then convert that rotational motion into linear motion on the actuator side of things. And in my experience, that gets a bit more complicated. You need like gears, or then another spool that the string... That could work. I don't know. Maybe. If the Bowden tubes had too much flex and too much backlash, then I do think that could be a good option, because then you could have the spool in there and have the strings wrapped directly on that spool, so that way the strings are not super long or having to go through Bowden tubes or anything. That's an interesting idea. Do you know, can you just buy those? I haven't actually looked at buying those like flex shafts. But that is a good idea. I will consider that. Yeah, James says backlash is bad. I agree. Position sensors for feedback would become critical. Yes. That is one aspect that I would like to add on here, but I'm not sure of how to do that, because my naive thought before having done all of this linear actuator testing that I've done over the last 2 weeks would have been to use a linear slider exactly the same as what I've done for this testing, but they're very bulky. They're a lot larger than I would have hoped, and they're a pain in the ass to work with. To be honest, you've really got to constrain them perfectly. If anyone knows of any way to sense linear motion accurately that's small, I would love to know, because I agree with James. That's a big aspect that this design is missing. That actually reminds me, one massive thing that I am very eager to change is the way that these actuators home and the way that they know their limits. Because this foam business is cool, but it just doesn't... It's not precise enough. It's really not precise enough. And like, there's no feedback up until right at the very end. The only feedback that the actuator gets in terms of its position is, oh, have I hit something? Oh, that's not good. I'm probably at the end. And yeah, that's not a good way to go. So what I'm thinking of doing instead is, I haven't modeled these in, of course, but what I'm thinking of doing is having on both ends 2 limit switches. One limit switch. Let me see if I can... I don't know where my limit switches are. This is the problem with having so many bits, is that I've got to like scan my parts boxes to find them. Yeah, okay. You can imagine it. Hopefully, in case you don't know what a limit switch looks like, it's like a box like this, and there's a switch up here. And if you press down on this, then that bends down, and there's like a little button thing in here. And there's various versions of these, but these are the ones that I've got. So that when you push this down enough, it will push down on this button, and then once that button is pressed, then it will know that the switch has been pressed. So what I'm thinking of doing is having 2 limit switches for each end, one of which would be... Let me draw this for you. So there'll be one limit switch. Come on, let me draw. It's highlighting. So one limit switch would be in here with a thing like this, and then the other limit switch would be like this, with the switch like that. The first one would be a warning saying, hey, you're almost at the end. You're about to hit the last point. But the actuator will be able to continue past that, because this switch will just be pressed down, and then it will just be sliding against that inner surface in there. Of course, we would need to make sure that it doesn't get like caught like a barb on the other end of this, but that's not an issue, I think. Then the actuator will be able to continue going until it hits this second switch, and I'm thinking that we can just route the power to the motor through that switch. And that way, if it ever hits that switch, then the whole thing will have to cut off. It doesn't have an option. Like, its power is gone, potentially. Or something to that effect, where it just basically shuts the actuator off. Of course, having it turn the power off is a bit drastic because it means that I'll have to manually go over there to remove it off the switch. But yeah, I think something to that effect would be fantastic, because that way this switch, as long as I don't move it myself, it's going to stay there all the time. And like there's like no force ever going onto it. So it's not like the current foam things where the foam is going to compress more over time. This is going to stay in the exact same position. The only thing that's ever happening to it is that this tiny little, very easy to flex switch part is just getting compressed, and that's it. And yeah, in my mind, this will lead to much more precise homing. What do we got? Decoder and Joe have suggested laser flight time measurements, or ultrasonic or laser. I have tried ultrasonic measuring, like linear measurements in the past, and they are good in the ones that I've tried at least, are good in very specific situations, but they're not super precise. They're not like millimeter precise. And I think that I would want that. Laser, I had a quick look at laser measuring systems after the stream last week, and I couldn't find anything that boasts millimeter level precision that's not like $4,000. So I'm not sure. If you guys know of any specific devices that are good for this, I would love to know, but I couldn't find any. It was only a quick search that I had, so it's possible that I just didn't look for long enough. But yeah, I do like that idea of having like a remote, like it'll be such a small component to do that measuring. I like the idea of that. Nebby says, put contacts on the rails and treat them as a variable resistor. That's interesting. I'll have a think about that. Yeah, it's interesting. It's interesting. James says, a rotary encoder on an independent slider along with a limit switch. Yes, I have thought the same thing, but then in my mind it just becomes like the same as the input actuator. Like if you have a spool with a string that makes the actuator extend and contract, and then you have a spool with a string that is measuring the actuation of the linear part, it's kind of the same thing. I get that you don't have that wind up backlash that we're seeing in the current actuators, but you might get the kind of opposite of where the actuator starts to move, but then the string that attaches to the measuring rotary encoder then also extends and whatever. Rotary encoder means yes, yep, decoder, I agree. It would need to only couple to the actuator position, not the drives. What is RE? Oh, rotary encoder, okay. A second string spool connected to a rotary encoder should give you better linear position with less of the tension bias and backlash issues, since the motor isn't pulling on one side. That is true. So that's Scott Bez, I agree. Because you don't, like the rotary encoder has like effectively no inertia. So there will be very low tension on that string. And maybe if it's all there, like if it's all on the actuator, then we could potentially use belts, which for the measuring side of things, which would hopefully stretch a lot less than the strings would. James says, or with a belt and tension pulley, we're on it. Or use that retractable cord at the base around the rotary encoder, then attach to the slider. Put the rotary encoder on the moving part. That could be interesting, with like a little wheel that runs along. That actually could work. Having a rotary encoder on the moving part with like I've got these little, where are they? Yeah, like this sort of thing. I've got various types of these sorts of bearings that are like designed to like fit into the linear slider. Really, let me show you on the end. So they fit like perfectly in that groove in there. So if there was like a tensioning mechanism to like keep that in contact, and obviously we probably want to use this one because this one's slippery as, but that could work. I like that idea. It does mean that there would have to be some more like big stuff inside here though. Yeah. I think I like the laser option the most if they were precise. Yeah, rack and pinion, yeah, no slip involved there, definitely. Time of flight 400F with the first time of flight sensor that comes to my mind, but definitely can't remember the exact accuracy. Sub 1 centimeter, that's decent. Joe has a very good point. If the rotary encoder is on the moving part, then I have to deal with wires. Yes. Yep. Yeah, there's definitely lots of options. Yeah, I think it's I'll start a thread on Zulip about this, and we can talk in more detail there. Yes, so the two options that I've talked about so far are both string actuated, but I think it's very reasonable to then go out onto a belt actuator. Of course, this would mean that the motor has to be on the actuator itself, because belts cannot flex in the same way that strings can, unless we use one of the flex spline ideas that Joe was suggesting before, which could potentially mean that you could have the motor off somewhere else and the whole thing would still be belt driven. I'm a little bit triggered still from my last experience with the belt drive, where I just could not get the tension to work nicely. My first foray into belt drives was not hugely effective, but I think that if it's implemented properly, I think that this could work really well. So I think we could just have like pretty much exactly the same thing as what we have here, except this spool would be like a toothed drive pulley. We would need some idler pulleys on either side to keep the tension on that drive pulley. But then other than that, it's the same. These are literally belt idlers. Like, that's what they are designed for. And so everything else would be the same. Like the belt would just connect onto this part in a similar way to how the string would, and would be very, very, very similar. One difficulty is that this tensioning mechanism probably wouldn't work, well, almost certainly wouldn't work as well, because with a string, you can obviously get the hex driver into here to actually actuate this bolt, but with a belt going across that covers up this entire width, I think it'd be a bit harder to get the screw in there, or the driver in there. So we'd probably need to have a slightly different tensioning mechanism, or at least change the way that this is forced up. I could just do it by hand, just like manually pull it out and then tension the side ones, but I don't think that'll be nearly as effective as this. Like, having this bolt drive this part out is very clever. Big kudos to John for coming up with that. Yes. So this is all one variant of this actuator that I'm imagining. And to be honest, this actually wasn't even the main one that I was thinking of up until when I started to CAD it, and I was like, actually, we can do this slightly differently. What I was thinking of doing before was actually having the linear slider mounted to the aluminium extrusion by the slider itself. So what I mean by that is, let me get some things. What we've been doing so far is having the linear slider attached onto the aluminium extrusion like this, and then this part, as it moves up and down, is what the end effector is attached to. But a different way to do this could be to flip this around and have the slider attached onto the aluminium extrusion, and then the end effector would be this rail. So if this is attached right at the very end, I've got little stoppers on here so I can't extend it the whole thing off the end. But if you imagine, like, this would be the linear actuator. And that simplifies some things quite a lot. It does introduce other difficulties, like how do you get the top string that comes down over here? Both of the ends of the string or the belt that's actuating this would need to attach to the bottom of the linear rail. The bottom one is obviously easy because you just come up from the bottom, but the top one would have to go potentially through that little tiny gap in the aluminium extrusion down past the block all the way down to the bottom. Potentially that would work, but there's not a whole lot of room in there. And it would mean that there's nothing that could be bolted onto this side of the aluminium extrusion so that the string would run into it. I think that this could work really nicely. It would definitely simplify things. It would massively reduce the parts list. It would, of course, not have nearly as much moment strength, like torsional strength, but axial strength would be identical. So if it was used in an application like what I'm using with Jugglebot, where there shouldn't be any, we should never have the case where the actuator is up like this and the whole thing is trying to be torqued around like that. That should not happen because it's all ball joints and universal joints. So that sort of force cannot really be transferred into the actuators as I have them in Jugglebot very effectively at all. So yeah, I'm very interested in this. I think it could work really nicely. Something that kind of turned me off of this is that I was hoping that this whole suite of new linear actuators would be scalable from the small side all the way up to the big side. And once I got those massive chunky linear guide rails that I used in the testing rig, I realized that the weight of these rails is not always as small as it is for these tiny little linear rails. For this one, I think that the weight of this rail is small enough that it wouldn't, for Jugglebot's purposes, it would not affect the acceleration that I can get out of these actuators. So I think it will be fine. But for those massive, like the, what was it, HG something 20 linear guide rails, that rail is like a good couple hundred grams. Like it is heavy for a 500mm long one. It is very, very, very heavy. So it would be difficult to get high acceleration out of that. But then also, like if you're doing something that requires something that large, you probably don't need super high acceleration anyway. So yeah, could go either way. Yeah, so what I'm thinking is there's a couple reasons why I want to make these new linear actuators. One is to the main one is because I feel that that would be the best way to let me start that again. In all of my YouTube history, my linear actuator videos are like 1, 2, and 3 most viewed videos, as far as I can remember. It's the last time I checked. The third one is this, like, way back. That was like the OG linear actuators with like the stepper motors and the ball screw and everything. For a long time, that was the third one at least. I don't know if it is anymore. But I think that making a new linear actuator design, especially one that is this adaptable with an Onshape file, I'm imagining having like an Onshape document that has like configurations, so you can just go in, you can say, I want to have an actuator that is X millimeters long. It has a square or a round end effector tube, and it uses this size linear rail, and it is belt driven or it is Bowden driven with the strings. I think it would be an interesting experiment and a good test of my Onshape abilities to make such a document. Then also, I imagine that would be hugely useful for people. And because these actuators will presumably be a shitload better than the ones that I've currently got, they will be, yeah, very enticing to lots of people. So hopefully that video will go really well. And that would mean that it's more, I don't know. I really want this whole YouTube thing to go well. And I think that that's a good avenue to achieve that pathway. I have been needing to work. I've got like I haven't actually mentioned this ever before on YouTube, but it may not come as much of a surprise, but I do have an actual job outside of YouTube. Even though I would love to be able to do YouTube full time, it unfortunately cannot pay my bills right now. So yeah, it would be really nice to be able to kind of, I don't know, push this YouTube thing further. And I think that these linear actuators are a good way to do that, I think. And also be fun. It'll be cool to see. The cherry on top of all of this, in my mind, is that I have, for a very long time, since I really started making these dual platforms, I've really wanted to make one that I can sit in and it can move me around like a little motion simulator. Probably wouldn't be very little, but yeah, I think that would be amazing. I don't really know if I have the space for it in this room, but you know, when there's a will, there's a way. Yeah, I think that would be very, very, very fun. And I think that'd be a good thing to play around with. So yeah, that's my thinking on these new linear actuators. Of course, all feedback is very welcome, and I appreciate any that anyone gives. There is one other new thing that I have not talked about in a little while at least, which is the ball primer. And what I mean by primer is something that can both start Jugglebot juggling multiple balls and also add more balls in once Jugglebot is going. So you probably remember that in my last main proper video, Jugglebot was able to juggle 2 balls in like one hand and juggle 2 balls by itself. But the way that I had to start that off, because obviously you can only hold 1 ball in its hand at one time, the way that I started that off is it would throw, it would then move over to its like second throwing position, and then I would manually place a second ball onto the hand within like a half a second time window, and then it would continue going. And the error rate on that was like 80%. It took many, many tries to have me be successful in placing the second ball in at just the right time. And that is not at all a tenable approach. It's not going to work, especially scaling up. Like if there was 3 balls, my time window for getting that third ball in would be even smaller again, and it just would not work. So we need some other, actually I'll get back to this. So we need some other way to get the balls into the pattern and yeah, to get it going with multiple balls. There have been quite a few really good suggestions for this. The second suggestion that I like the thing that I think is that I would do if I wasn't doing what I'm about to show you is to have a rail up the top. And I've even got, you can see like where I've got the black and the white paper rolls, just like here and over here, there are two more hooks, and I could have a third rail below that, and I could have a fairly straightforward dropper. And that's, you can see that's like directly above where Jugglebot is. So I could have a little dropper on there where there's a bunch of balls lined up, and there's like a little servo motor or something. I can just press a button, or it could be automated, like connected to Jugglebot's brain computer, and then it can just say drop now, or drop now, or drop now, and it would just drop the balls in. I do like that idea, but I don't love it. I think it has a couple problems. One of which is that that whole system has to be higher than the highest thrown ball by Jugglebot, because of course if it's directly above Jugglebot, like 50 millimeters above, then that's going to get in the way when future balls are thrown. So it has to be above the highest throw that Jugglebot will ever make, and that kind of limits how high Jugglebot can throw. Especially in a space as small as mine, I really want to be able to like push the limit like right up to the ceiling, and I don't want to just cut out like half a meter of throw space just for this thing. We could potentially move it off to the side so that the Jugglebot's not throwing balls in that direction, but I don't know. I don't think that would work super well, because that would mean the Jugglebot would have to like throw, zip over here to get the next ball, and then zip back. And yeah, I question this current robot's ability to do that sort of thing. Yeah, it's also very dependent on this space that I'm in. Like once I move houses, I will probably not have the exact same sort of setup as I do right now, and that sort of priming mechanism will probably not be very like exportable to other spaces. So what I would like to do is have something like this, where this is obviously a very, very rough model. So yeah, don't judge too hard. Again, there's also a link in the description for this CAD file if you want to check it out. You can give me a thumbs up with the first one. So the idea here is that this base can rotate around relative to the ground, and then this part can rotate on this second wheel, and then this hand actuator is identical to the current one on Jugglebot. It's just a bit shorter because it doesn't need to be able to throw the ball like 5 meters high or anything. My thinking is that this can sit where my head is in the way, where my gimbal currently is, right here on this corner of the desk. So it will only need to throw the ball like half a meter high. It just needs a bit of like horizontal travel so that it can reach from there over to where Jugglebot is. But this should be very easy to move around. Like this could be on the floor next to Jugglebot, and it could just pop the balls in. And I'm a big fan of this. I got these Eagle Power motors. I believe they're the ones that Ayed Musa used in his capstan drive video, and they're so nice. They're so sexy. But unfortunately, I haven't been able to get them to actually spin. It's teasing me so much. Like I've got it set up. I've got my encoder on the back, but for some reason my encoder isn't sending signals for some, yeah. I need to work on this a bit more, but I love the way that these motors look. So my idea is that I would have one on this part to rotate this thing here, and this would be a capstan drive, very similar to what Ayed Musa showed. So the string would wrap around here like a proper capstan. It just wraps. It's not actually tied onto the spool at all. And then the string will be fixed onto this block, and on the other end, oh, here you go. You can see I've made some progress to getting that locked off. I'll explain what this zigzaggy star thing is in a sec, but the string will be locked off here, and then as this motor spins, it spins the spool, which then rotates this thing along its curve. Now, of course, as this is right now, this would amplify any error that this motor has by the end effector. So like if this motor was like 1 degree off, it would mean that the position that the launcher is actually throwing from is going to be like 15 millimeters or some large number of millimeters off, because it is so much further away from the center of rotation and where like the torque is being applied. So I think a better way to do this would be to have the motor right at the very end, so that the whole thing, so like the thing that is making this rotate is as far away from the center of rotation as possible, so that way all of the error is minimized, basically, to be as small as possible. And I don't think that should be too hard to do. I could also put, and it would probably put, a rotary encoder on this entire assembly itself, so that I can actually measure the exact position of this arm rather than relying on the motor and the capstan drive, just to get a bit more feedback and to get it extra precise. Now, yeah, actually just quickly, this little star thing is, let me just grab something. I'm glad I kept this. I've been umming and ahhing. Oh my goodness, it's covered in cat hair. It's been a while since I've taken this out. But this is something that oh wow. Yeah, this is something that I made a little while ago, and the idea with this zigzaggy thing is that inside that there will be a little kind of, I don't know what you call that, a weird kind of gear, and with this gear, it's like a one-way pulley almost. So the string is fixed onto the end of this, and as you spin it, you can spin it in one direction, like it's mirrored this way. You can spin it this way, or yeah, you can spin it one way, and it will go and it will click, but it can't spin back the other way because all of these like veins on this gear get stuck in the teeth. And I have been very surprised at how well that has worked. It is very, very, very strong. You can really tension it up quite a lot. And so the way that I did that tensioning is, you can see on this pulley, there's 3 holes. In those 3 holes was like another mating piece, and so that just goes in with like 3 bolts, and then I can twist that mating piece up and then remove that mating piece out, and then it's locked in. If I ever want to remove it, I can just loosen that bolt in the middle and then slide the whole thing out, and all of the tension goes away. But like, I tensioned this and made this probably almost a year ago, and like, it's still tight, like super tight. Like, there's no way I could tension the strings that much by hand. I've been very, very, very happy with how it worked. For reference as well, I was trying to increase the, I don't know what you call that, like torsional rigidity of this, this was supposed to be like the bottom of the platform of Jugglebot. And so the idea is that, like, having these strings here, obviously we would want them like as far out as possible, so that way the torsional rigidity is increased. But obviously I haven't moved forward with this because it's just too complicated and doesn't really work super well. But the tensioning thing does. So my thinking is that I would use the same tensioning mechanism in this guy. Now, one other aspect of this that I am a big fan of, and I am curious to see people's opinions on, is the way that I've got it open here. The way that this base part would rotate. And there's obviously a lot of ways to do it. The easiest one would just be to put another one of these motors, I got 2 of them, put another one of these motors on the bottom here and just have it directly drive the this lower plate. And that would probably work, but it's a bit lame. And yeah, I think it'd be hard to get super precise movements. I kind of want to gear down these motors a little bit so that I can get it to be as precise as possible. So my thinking is that I can make something like this, where the motor has a 20-tooth driven pulley. This is going to be belt drive. The belt would wrap around this pulley, on both sides obviously, wrap around these idlers, and then somewhere on the back here get fixed onto the other end of the spool. And so when the motor spins, it will spin that, it'll spin the driven, like the 20-tooth pulley, and then it will make, like, for example, if it's rotating this way, it will shorten the, let me actually draw on this. Hopefully it makes sense. So for example, like, let's say the belt is fastened there, it goes up, around, 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 and then it's fastened onto here. If the motor is spinning in this direction, then that will act to shorten this length of belt. And that would mean that the whole thing has no choice. So this would have to be fastened like onto the ground as well, like below this plate. That would mean that this has no choice but to rotate this way. And then of course it works in the opposite direction as well. Now, the big problem with this design is that it means that the belt will be sliding against this surface along here. And I didn't realize this until I had cutted everything up. And I was like, oh, no. Like, I obviously recognized it a little bit, enough to know that I should have these pulleys on here, but I didn't realize that the belt is actually going to be dragging along the main surface along here as well at the same time. Well, I guess more properly, this surface will be dragging along the belt because the belt will be fixed. But I don't think that that should be too big of an issue, because I have this ultra high molecular weight tape, which is very, 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 very slippery. And I'm thinking that I can just put that along that surface, and the belt would just rub along this, and hopefully it should be a non-issue. Hopefully. Yeah, so yeah, that's where I'm at with that. And again, same as linear actuators, this does need a bit of work, but I'm going to try to kind of make slow progress on this over, like, I don't know, evenings here and there and like weekends and stuff to get this going. Because this is obviously not the main focus. Like, I'm going to be spending most of my time on Jugglebot proper, but both of these two things are kind of like lingering in the background. And same as the linear actuators, the reason I'm bringing this up now, even though it's at such an incomplete stage, is that if anyone has any ideas, I would love to know. And I mean, if anyone is like really, really loving either of those two things and wants to contribute to them, I would love that too. Like, I don't really care if I am the person to make these things. I just want these things to exist. So yeah, take that how you will. Joe says, put the motor in the base and have the platform turn above it, ends of the belt attached to the platform. Are you saying like the same thing but flipped around? Because it sounds like it. Yeah, because that one concern with using this style of like base plate is that it would take up a fair bit of space on here. The main reason why I wanted to have this motor in the profile of like this base plate, by the way, rather than having it on the outside, which would be the easiest way to do this. Like, I could just have the exact same capstan drive mechanism that I have here, but on the bottom. I just don't want it to take up too much space. I would like the top down, like this profile of the whole thing, to be as small as possible when it's vertical. Like a record player. I actually don't know if I know how record players work that precisely, but I will have a look after this stream. Let's see. Put the motor in the base and have the platform turn above it. Ends of the belt touch. Yeah. Yeah, okay. It sounds like he's suggesting having the motor off to the side, so like if I draw on this. Yes, only the motor shaft about half. Yeah, okay. So the motor shaft would be here, and like the motor would be like here, sort of thing. So this would run along like that. Yeah, potentially. And because that's not moving around, the increase in size wouldn't be too big of an issue. But I don't know. I'd like it to be as small as possible. Yeah, that would definitely be mechanically a lot simpler. Yeah, oh, my screen wasn't showing, and I just deleted it. Whatever. I get I get what you're saying. Okay, yeah, bit of friction, and we can probably just use ultra high molecular tape. And yes, as I said, I think it would be a good idea to move this motor actuation right to the very end, just so that it's a bit more precise. Now, there's one other thing that has happened this week that I'm sure many of you are probably aware of, and that has taken more time out of my week than it probably should have, which is that Bambu Labs has come out with a new printer, the H2D. And yeah, I've spent a lot of time looking into this and thinking about what I could do with such a device. And I am very, very, very on the fence for getting this. I'm just kind of like letting it sit for a bit. I don't want to jump into any big purchases, but man, am I tempted. For anyone who is unaware, this printer is basically like the old Bambu one, just better. It's bigger. The speed is effectively the same as far as I'm concerned. The spool thing at the top can actually dehydrate your filament, which I love the idea of. The main thing that is like causing controversy is the fact that this you can buy as like an add-on, like a laser cutter thing. I think that's a terrible idea. I don't know why they decided to do that. I think the laser cutter it's just like, there's health hazards, there's like gunking up your printer hazards. It's just, I don't know, not a good idea. Yeah, but I do really like the idea of being able to print two materials at once. I've been thinking a lot about how I could integrate TPU into PETG parts or like other material parts. To, for example, one thing that keeps giving me the shits is that in the hand actuator, to stop the hand from running, like to stop the linear rail, to stop the slider from running off the end of the rail, we have these little bumpers on the ends, and these are just secured with a single, I believe, M5 bolt. But of course, this slider can get a fair bit of inertia when it gets going. So it is not uncommon for these bumpers to slowly get pushed back further and further and further. And of course, unless I go over there manually and visually inspect it, I don't know that this has happened. And actually, when I went through and replaced the hand spool, when I replaced the printed one with the aluminium one, I noticed that the bottom bumper was like way off the end. There was like a 5mm gap between the rail and the bumper, which is probably getting pretty close to the point where balls might fall out of the slider, which I really do not want to have happen, because putting those balls back in there is like impossible. It just does not work. So I'm thinking that if I could print a strong material like PETG for the bit that's like being fixed into the rail, and then have like a little TPU bumper attached to it, so that way that TPU bumper would take the brunt of that force without actually making the bolt part have to shift at all. I think that'd be very cool. And also being able to print these bellows again. I saw in one of the reviews of this printer that someone had printed these little like, I don't know, like air puffy things. It was like a rigid base with a bellows on top, within like a funnel on top of that. So that way you could squeeze the whole thing and it would like squirt air out. And it was like literally the same bellows as these, but it was like perfect. All of the lathes were perfect. It was so crisp and clean. And I would love to be able to have that. It'd be good. So yeah, I've spent many hours this week doing research into this printer, and I'm this close to getting it. So I mean, maybe next week you might see me with it. Yeah, fancy machine, but Bambu and the requirements to connect to them bothers me. Yeah, I get that, but it seems like their slice is pretty good, and I don't. It seems like the issues with all the firmware stuff, that seems like it's mostly an issue if you want to kind of like run your own slicer and like do your own sort of things. But as far as the actual, I want the machine to be purely just a machine. I want to be able to create a file, send the file to my printer, and have it print. I don't really care, as long as I can do that like remotely. I don't really care too much about getting too fancy with that whole process. Yeah. Yep. I think I had a couple more things to say on that, but yeah. Oh no, actually the big one is that I've been since I've become aware that this printer is a thing, I've been looking at and like when I put Jugglebot back together again, I just noticed how crap the print quality is with a lot of my parts. Like this is a pretty normal occurrence for my current printer, and there are so many parts, like all of the parts on the linear actuators, maybe actually not all of them, but a lot of them, I had to go to a lot of effort to make sure that they printed nicely, or like could be printed at all, in terms of like having no overhangs and all that sort of stuff. And the quality of those is not fantastic. It obviously works, like it's just surface quality stuff mostly, but yeah. I'd be very keen to like print like a full actuator with the new printer and see if you can actually get it perfectly, because some of the parts are pretty hard to print. Some of them are very complicated. Yeah. Yep. So that's where I'm at now. I've spent a lot of time on that. Yes, it's fun to dream. It is. And actually, a big important thing on that is that I almost have enough money from YouTube ads and Patreon. Thank you to all my patrons. Almost have enough to pay for that outright just with that money. So it's like pretty much just YouTube money, almost. I would need to just top it up a little bit with my own money, but yeah, it's pretty cool. Yeah, big thank you to all my patrons and to all you for watching my videos, giving me that sweet AdSense. Yeah, cool. All right, that is it for today, I believe. Hopefully next week, fingers crossed, we have that nice smiley face in the thumbnail. Yes, I'm very keen. All right, cool. I hope you're all doing well, and good luck with everything you're doing. And I will see. Oh, I keep forgetting to check my calendar. I'm pretty sure I'm free next week, so I'm pretty sure I'll have a stream next week. So yeah, I'll see you then. Till then, have a good one.